In this video, we are going to discuss Fourier series. Fourier series is an important method for solving the problems of heat conduction. Especially in electrical engineering, it is used for the analysis of current and voltage in alternating circuits. It is used in electrodynamics, acoustics, and etc. The basic idea is to represent the periodic functions by a series involving two trigonometric functions whose periodicity 2 pi they are sine and cosine functions. We find expansions of even and odd functions in an interval of length 2 pi, and later we can expand given functions in an arbitrary interval whose length 2l. We develop half-range Fourier sine and cosine series also. Now we shall discuss the periodic function. What is a periodic function? A function f of x is said to be a periodic function if a function at x plus capital T is same as given function for all x belongs to the given interval and T is least positive number, then T is called the periodicity of a given function f of x. For instance, one can consider a function f of x is equal to x that x belongs to the interval negative pi and positive pi. You can see the graph of the function f of x is equal to x over the interval negative pi and positive pi. It is symmetry about the origin. Why? Because it is an odd function over that interval negative pi and positive pi, and it is extended to some other interval. You can see the graph. Let us see some examples regarding a periodic function. The function sin x has periods 2 pi, 4 pi, 6 pi, and so on. Since sin of x plus 2 pi equals to sin x, sin of x plus 4 pi is also same as sin x. Sin of x plus 6 pi became sin x, so that sin x has periods 2 pi, 4 pi, and 6 pi, and etc. Coming to another example, if the function f has the period capital T, then the definite integral one can see integral a to a plus t f of t dt is same as integral 0 to t f of t dt, where a is a real number. So you can remember one of the key point regarding this Fourier series is Fourier series is an infinite series representation for periodic functions in terms of two trigonometric functions, sine and cosine. Now we are going to see Dirichlet conditions. Here one of the very important observation regarding Dirichlet conditions is not every function can be expressed as a Fourier series. Peter Dirichlet derived a set of sufficient conditions but not necessary conditions. You can see them. The function u of t must satisfy, first of all, it is a periodic and single valued. Second one, it is bounded absolute integral, that means integral over 0 to t. The absolute value of the function u of t is less than positive infinity, and it has finite number of maxima and minima per single period. Moreover, it has a finite number of finite discontinuities per single period. Now one can see functions which have no Fourier series expansions. For example, a function sin inverse x that is defined on the interval -1 +1. The length of interval is 2, but it is not single valued. Hence, one can conclude that this function sin inverse x not valid for the Fourier series expansion. Coming to another example, a function tan x that is defined on a finite length of interval 0 to pi, it has infinite number of discontinuities, especially at x is equal to pi by 2 and 3 pi by 2. You can see the graph of tan x, and it has infinite number of discontinuities. Another example regarding functions which do not have Fourier series expansions. Here the function is the sine of 1 upon x that is defined on interval -2 pi positive pi. It has infinite number of maxima and minima, especially in the neighborhood of x is equal to 0. Just you look at this particular graph. From this, one can observe that Dirichlet conditions are only for the existence of Fourier series. These are sufficient conditions but not necessary conditions. It means that a function doesn't satisfy the Dirichlet conditions, it may have a Fourier series expansions. That is one of the very important observation regarding functions which have no Fourier series expansions. Let us see which functions are good functions for the existence of Fourier series in a finite length of intervals. One of the examples, sin x or sin t, it is one of the best function for the validity of Fourier series expansion. Coming to another example, that is x square or t square, it is also well defined function for the existence of Fourier series in a finite length of interval. Coming to bad functions, tan x or tan t, it is not a good function for the existence of Fourier series since it has infinite number of discontinuities. Coming to sine of 1 upon x or sine of 1 upon t, it is not a good function for the existence of Fourier series since it has infinite number of maxima and minima in given finite length of intervals. Let us see Euler's formula, which is used to find the Euler coefficients a0, an, and bn for the Fourier series of given function in given finite length of intervals. Let f of x be a function that is defined on L plus 2 pi, where L is the lower limit, L plus 2 pi upper limit of the interval. And first of all, we have to know the Dirichlet conditions. F of x is a single valued and bounded function. It has at most finite number of maxima and minima. It has only finite number of discontinuities per single period. Moreover, it is a periodic function. Now, the Fourier series expansion of f of x on the interval L plus 2 pi a naught upon 2 plus the sigma n is equal to 1 to infinity a n cosine nx plus the sigma, the index n vary from 1 to infinity bn sin nx. It is an infinite series representation of two periodic functions, cosine and sine. It involves only cosine and sine. So how to estimate a naught? A naught is measured as 1 upon pi integral L to L plus 2 pi f of x dx, where f of x is given function ln L plus 2 pi lower and upper limits of the interval. Coming to an, 1 upon pi integral L to L plus 2 pi f of x cosine nx dx, where f of x is given function, cosine nx is the quotient of an that is already mentioned in the Fourier series. Coming to Bn, 1 upon pi integral L to L plus 2 pi f of x sin nx dx, where f of x given function sin nx is the quotient of Bn. So what is the main advantage of this Fourier series? Discontinuous function can be represented by Fourier series. The derivatives of discontinuous function do not exist. It is not true for Taylor series. That is one of the biggest asset by this Fourier series. The Fourier series is useful in expanding the periodic function since outside of the interval there exists a periodic extension of the function. That is another important observation regarding the advantage of Fourier series. Coming to expansion of an oscillating function by Fourier series gives all modes of oscillations, which is extremely useful in the physics. So Fourier series of discontinuous function, it is not uniformly convergent at all points of the interval. So one of the major advantages of Fourier series, term by term integration of a convergent Fourier series is always valid. It may be valid if the series is not convergent. Now we are going to see the Fourier series expansion of given function f of x that is defined over the interval negative L positive L. The Fourier series f of x equal to a naught upon 2 plus sigma n is equal to 1 to infinity a n cosine n pi x upon L plus the summation, the index n vary from 1 to infinity bn sine of n pi x by L. So it is the infinite series representation in terms of sine and cosine. Now you have to find a naught, a n, b n Euler coefficients, where a naught equal to 1 upon L integral negative L to positive L f of x dx, where integrand is a given function f of x. Coming to an is estimated by 1 upon L integral negative L to positive L, the integrand here, the product of given function f of x and the coefficient of an. And bn, that is estimated by 1 upon L integral negative L to positive L, the integrand here, the product of the quotient of bn and given function f of x. Later we are going to see functions having points of discontinuity. For this, let f of x be a function that is defined by phi of x when x lies between alpha and c, psi of x when x lies between c and alpha plus 2 pi. Here one can observe that c is the point of discontinuity to the function f of x over the interval alpha and alpha plus 2 pi. That means it has a finite number of discontinuities. Now you can see the graph of this function f of x. X equal to c is the point of discontinuity. You have a phi of x over the interval alpha and c. Between c and alpha plus 2 pi, you have a psi of x. Our main objective is how to write the Fourier series expansion of this kind of points of discontinuity containing functions over the interval. It has a finite number of discontinuities. Now we are going to see the Fourier series expansion to this function f of x. It has a point of discontinuity at x equal to x naught. Here f of x is defined over the interval L to L plus 2 pi. The Fourier series f of x a naught upon 2 plus summation, the index n vary from 1 to infinity a n cosine nx, where a n is Euler coefficient and it is a coefficient to the one trigonometric function cosine nx plus sigma n is equal to 1 to infinity bn sine nx. Here the function f of x has a point of discontinuity at x equal to x naught. Now a naught can be estimated as 1 upon pi integral L to x naught phi of x dx, where integrand phi of x is defined over the interval L to x naught. The second different integral will be integral x naught to L plus 2 pi psi of x dx, where psi of x is the second function that is defined over the interval x naught to L plus 2 pi. What is an? An is estimated by 1 upon pi integral L to x naught phi of x cosine nx dx. Here the integrand is the product of the first function that is defined in the first section of interval with the coefficient of an, and the second definite integral will be integral x naught to L plus 2 pi, where integrand is the product of the second function and the coefficient of an. Coming to bn, that is estimated by 1 upon pi integral L to x naught phi of x sin nx dx. The second definite integral will be integral x naught to L plus 2 pi, where integrand is the second function that is defined over the interval x naught to L plus 2 pi and the coefficient of bn. So mainly we have observed that this function f of x has a discontinuity at x equal to x naught. The Fourier series expansion of this kind of functions may converge to half times of f of x naught negative 0 plus f of x naught plus 0. We are going to see some important formulas and you can remember them. First of all, the definite integral negative pi to pi cosine mx cosine nx dx, whose value is 0 when m is distinct with n. Coming to when m is equal to n and that equal to 0, whose value will be 2 pi. So when whose value is pi, the condition m and n are same and both are positive values. Secondly, you have a definite integral negative pi to pi sin mx sin nx dx, whose value is 0 when m and n are same equal to 0, or sometimes m and n are distinct, whose value will be 0. When m and n are same and positive, you have a pi value. Coming to another one, sin 2n times of pi by 2, that is sin n pi, whose value always 0. Sin pi, sin 2 pi, sin 3 pi, sin 4 pi, all these are 0 valued. Coming to next one, sin of 2n plus 1 times of pi by 2, whose value is negative 1 power n. When n is equal to 0, you have a sin pi by 2 value 1, sin 3 pi by 2, sin 5 pi by 2, etc. Now you can see cosine n pi, that can be expressed as cosine 2n times of pi by 2, whose value negative 1 power n. For example, when n is equal to 1, cos pi value negative 1, cos 2 pi value negative 1 squared, that is a positive 1. Cosine 2n plus 1 times of pi by 2. When n is equal to 0, you have a cos pi by 2. Cos pi by 2 value 0 itself. Hence, one can conclude that cos of 2n plus 1 times of pi by 2 value 0. Sin of 2n pi, sin pi, sin 2 pi, sin 4 pi, sin 6 pi, all values are 0. Next one, cosine 2n pi. for instance, we take n is equal to 0, cosine 0, 1. So cosine 2 pi, cosine 4 pi, all these values equal to 1, of course. Next one, cosine n pi by 2, based on the index n, it has two values based on the nature of even and odd. The first one, when n is even, it has a negative 1 power n upon 2. When n is odd, whose value 0 itself. Coming to sine of n pi by 2, and it has two values. When n is odd, it can be determined as negative 1 power n negative 1 upon 2, 0 when n is even. Now you can see one reduction formula. It is an indefinite integral whose integrand the product of two different functions. The first function is exponential function whose coefficient a, and the second function is a trigonometric function whose coefficient is b. The reduction formula will be e power x upon the sum of squares of two different coefficients times a sin bx negative b cosine bx. The second one, another indefinite integral e power x cosine bx dx, whose reduction formula e power x upon sum of squares of their coefficients a cosine bx plus b sin bx. Here one can observe that the signs occur due to the nature of the two different functions sin bx and cosine bx. Coming to another reduction formula, that is integral 0 to pi by 2 sin power nx dx equal to integral 0 to pi by 2 cosine power nx dx. It has two different values based on the index n and its nature. First one, n negative 1 times of n negative 3 times of n negative 5 until some constant comes upon n times of n negative 2 times of n negative 4 until some constant presented there. This is possible when n is odd. Coming to second one, and the same result occur, but it has a some factor, that is a pi by 2 when n is even. Important reduction formulae, integral 0 to pi by 2 sin power mx cosine power nx dx. Here the integrand is the product of two different functions sine and cosine whose exponents also different. They are m and n. It has two different values based on the nature of m and n. Now the first result, m negative 1 times of m negative 3 until some constant comes. This is only based on the exponent of the sine function. And coming to the second function and its exponent, you can see n negative 1 times of n negative 3 times of until some constant comes upon. Now you can see in the denominator, the resultant denominator will be, you can add the two exponents for the two different trigonometric functions sine and cosine, that is m plus n times of, you can see the decrement in m plus n is 2, m plus n negative 2, m plus n negative 4, proceed in this way until some constant presented in the denominator. This is possible only when m and n are not simultaneously even values. So later you have the same result, that is multiplicated with pi upon 2. This is possible only when both m and n are even values.